We're continuing our lecture. We're deriving Euler's rotational, what we're going to call here when we're done, Euler's rotational equations. We now need to deal with the term we call B. B was this integral of R cross omega cross R. Integral of R cross omega cross R. And for fun, we're pretending that we are we were Euler. We were there. So it's R cross omega cross R. R cross omega cross R dm, and the order of operation were like that. You need to cross those two. All right. Well, so, you know, what on earth was Euler thinking? Well, Euler might have been thinking this. He said, well, you know, I got this far with that triple vector product. So let's apply the triple vector product again, the triple vector product again. Now in this case, but I've got 4 vectors, not 3, right? So, you know, I don't know how many combinations he tried. I don't even know if he went this way, but we'll go straight to the chase. So let A equal R, the first term. Let B equal omega, the second term. And then let C now equal, I guess C has to be the omega cross R for this too, because we only have 3 vectors to choose. So if we do that, we now get the integral, and I'll just leave everything in here, of back minus cap. So omega times A, which is R, dotted with omega cross R, minus, that's the back term, minus cap, so C, which is omega cross R, times A, R, dotted with B, omega. Now, R dotted with omega cross R. R dotted with omega cross R. What do we think that is? Yes, it's 0. Omega cross R gives me a new vector that's perpendicular to both omega and R. At the moment, I'm going to care what it is, but I do know it's perpendicular to omega and it's perpendicular to R. R dotted with something that's perpendicular to R. That term goes to 0. And I'm left with, yeah, way to go. And I'm left with this next term. Now, this is the point where I have no idea how, you know, I mean, if this is the road they were going down, so we're left with this term. Well, the derivation that we use, again, I don't know how he derived it, but let's just pretend he's doing it this way. So we now get the integral of, and I'll just pull it out, negative omega crossed with R times R dotted with omega. And I can pull the omega out. All right. So I'll start pulling the omega out. So I get negative omega. Now here's the thing crossed with this thing, this term. He takes this term and says, well, I can do this. I can add, so we get an R, I guess I'm going to pull a plus inside. Sorry about that. I'm going to pull the minus here. So we had a minus R times R dot with omega. Okay, that's just a repeat. And he adds this term, omega times R dotted with R. Why can we just add this term? We're just adding this term. Yes, we're adding a 0 to the equation. Why? Because omega crossed with omega times the scalar is 0. We're adding 0 to this. So that's why it's that. We're adding 0. We're adding a 0.
You pull the omega out because it's independent of mass.
Exactly. It's independent. As I move over the body, the omega doesn't change. That's one very important concept, which you guys have down. But a body rotating, the omega is the same everywhere on the body. It's a constant for the body. Alpha is a constant for the body. All right, so now that I've done that, we can do the back minus cab rule in reverse. So we're going to, man, this back minus cab. I don't think well, I say that. I occasionally use it elsewhere, but I mean, this is probably the most use that a lot of dynamicists ever get out of back minus cab. So now let B equal omega, let A equal R, and let C equal R. Does that work? Back minus cab. So C, yeah, that works. So if we do that, we can sort of undo. So we get omega crossed with this integral. We can undo the back minus cab. So that means it's A cross B cross C, or R crossed with omega crossed with R. dm. All right. Now, at this point, I'm going to say eureka, right? And why is that? Do you remember just a minute ago, recall that we said the integral of R cross alpha cross R dm? Scan back your notes. We did that work. And we just showed that that equals I alpha. Well, alpha and omega are both independent quantities. It would be the same derivation. We would get then that R cross omega cross R dm is going to give me I omega, all right? I omega, the momentum, angular momentum. So that's the angular momentum of I. It'll, again, give you an equivalent derivation of the inertia matrix, and that will lead this term B to be omega cross I omega. And you know what? I need to do something actually very important here that I forgot. This I is about, everything's about the centroid. So that I is about the centroid, G. I is about the centroid. And those terms are written in, and the terms are in the body fixed coordinates. Okay, so it's about G and in the body fixed coordinates. Yes?
Right above where you have the BAC, why did you use the BAC in that?
Okay.
I guess.
So I don't know. It must have just been stumbling. Maybe I had some insight, but I really don't know how you get there. We had this term from above. We used this term. We added an extra term. And our justification was that we added in the omega cross omega. We just added this term right there. But now we basically get the simple vector product of the back minus capital and reverse. So this is B times A dot C. This is C times A dot B. Okay. So we're applying the triple vector product in reverse. We unwind it and get this side. And of course, you continue then we'll redo it. Honestly, how Euler derived it? I mean, did he do this? If he did this, it would be amazing. I mean, I guess that's the way discoveries work, What? Goats. Yeah. Yeah, no, yeah, exactly, yeah. Well, I mean, I will say, to some degree, these guys probably were benefited without a calculator because they, I mean, I would have a long time ago said, just plug in the numbers. You can't do anything with this, right? Just give me numbers and I'll tell you what the answer is. It is quite incredible, but this led to, really this fundamental rule that governs how things work, and that is, let's put it together, which is Euler's, which we're going to call Euler's rotational equation. So we get the sum of the external moments about D equals, now I'm going to write it down, we got dg cross m ag, that was the first term, plus these other two terms that we just derived. I G alpha, and I neglected to write the G in there. We'll probably go back up and do that. IG alpha plus omega cross IG omega. I mean, I guess it's nice that we can actually sit here and derive it in the period of the class. It's a fundamental thing, but it is, you know, and it built on a lot of math that we already had. So that is the sum of moments. So we get the sum of forces equals MAG. And, you know, I didn't go through, but you could go through sort of the same thing. You don't have to do the inertia matrix, but you can see that most of those terms go to zero. All you're left with is the MAG. I didn't do that. I guess I didn't do it, but you can see that. And then we get this term. So this is the Newton term. This is the Euler term. And those are our equations. These are equations of motion for a rigid body. In 3 space. A few comments, obviously, you know, we've done this, but it's good to put our notes. G is the center of mass. Some of the forces, some of moments are the, these are the sum of external forces and moments. That's kind of obvious. One of the big reasons I bring it out is that this IG is the inertia about the center of mass, or CG, about G, and it's in body fixed frames, body fixed frame. And that came from the derivation. You know, when you're doing that derivation, both alpha and omega had to be written in the body fixed frame. So I'll put it here. Alpha and omega are expressed in body fixed frame. So those are kind of the key terms. Okay. And then this term is called Euler's rotational equations. And then I guess the first one we call N2, Newton's second law, or I call it N2. Let me say one last thing, we'll take our quick break. The last thing I want to say, we've got these 3 terms, right? This term is the fact that you're taking the moment about, not the centroid. It's the lever arm you get from a body moving around something. Typically, frankly, I almost always write the equation about the center of mass. So if you take the moments about the center of mass, that first term goes to 0. The second term, the I alpha, that's natural. That's just a corollary to Newton's law. That equals NA, N equals I alpha. So familiar with that. The third term, you know, sometimes this is called, I say sometimes, this is what we call the gyroscopic effect. The third term is the gyroscopic effect. You've got a body that's spinning, you know, and if then that body spins, that creates a torque. We can see the torque. I mean, the moment is a torque. We can see the torque. The torque is orthogonal to the angular momentum. And the second term. Let's think of one really quick example for fun. Okay, this is just a really quick example for fun. Here, I'm picking on Tommy. Here Tommy is riding his bike into work. Where do you ride from, Tommy? So it's like a 2-hour pedal?
Probably, yeah.
Okay, we're going to upgrade Tommy to a motorcycle. Tommy's driving through the night really fast in the motorcycle, okay? So, you know, Tommy says to himself a couple things. Well, why don't I fall over? And then, you know, well, how is it that I steer this thing, right? So you've got wheels, and the wheels have inertia. So let's just look at the front wheels. The wheel has a big spin component, call it -1, and it's got inertia. So it's got a big I omega basically right there, right? Okay. So let's think what happens to Tommy when Tommy grabs a hold of the handlebars. And we can think about this in 2 different ways, but let's think about it. Here's Tommy. Let's say Tommy.
Kind of an odd concept on the motorcycle. So let's say Tommy he wants to turn left. He's going down the interstate. He wants to turn left. He's going to grab his wheel and turn the wheel. Turn the wheel to the left.
So he is going to create a second term to the omega. You know, they come together. I'll just call omega 2 like that, all right?
So you're going to recommend to Tommy not frankly do that, okay? So let's just see what so we might say why. You know, dynamics is why. Well, let's dynamics that. So effectively, you know, we can break it down, but effectively this is a big thing. We'll kind of do that one comes to our omega. But we've got the total omega. So this omega plus the omega. But in this term, this omega plus the omega is going to be non-zero, and that's going to give us a moment acting on the system. And what's the direction of the moment? Well, hopefully, as he turns, he's going to lean over the point.
That's how you really turn on a motorcycle. So we get this omega
Crossed with I omega. Right? So omega crossed I omega. So that means that to do that, you have to have a torque.
Omega crossed with I omega. So he's going to get a torque in this direction, or a moment or a torque in this direction, right? Now, so in other words, now this is always confusing, right? Because we're actually reaction, right? So we said you drive down the road, you physically rotate the string to the left. To do that, just to stay upright, that means there has to be a torque, you know, to the left. Is there a torque acting on you on your motorcycle? No. I mean, you just got point contact between the wheel and ground. There's no torque. So what's going to happen to Tommy? So he's forcing it to be dynamically in equilibrium. He has to have a torque. He doesn't have a torque. So what's that? He's going to fall to the right. Does that make sense? So he's going to fall to the right. All right. You know, that's not what he's going to do. Here's some kind of an interesting thing. If Tommy were to do the other way, and this is kind of what they tell you in the motorcycle. I remember testing that. They turn right or turn left, push, you know, push on the right hand. Yeah. So what you're doing is if you try to turn the other way, and you don't actually have to turn, you just start with, well, actually, I guess it'd be more of a torque. If you apply a torque, I guess that's what we're doing. Let's say this. If Tommy applies a torque, let's try this one more time. I wasn't clear on that. I keep changing my example. All right, Tommy. Now you're going to take our advice. You're going to apply a torque. And let's see which way you're going to apply a torque. Let's do the same thing. So now you're going to apply a torque about this guy. So you got a torque or a moment. So it's like you're applying a torque. You're not physically turning the wheel, but you're just applying a torque, right? So what would your omega need to be to stabilize that? So let's try. Let's see if you had an omega going this way. Yeah. With omega 2 plus I omega will give you that torque, okay? So if you apply a torque this way, you're going to get an angular velocity this way. You're going to lean to the right. So if you apply a torque this way, you're going to lean left. If you want to turn to the left, you've got to apply a small torque, right? That'll cause your whole bike to lean to the left. The wheel's not going to lean. Apply a torque. Yeah, basically got to do the opposite. And that's actually a problem with beginners. You know, they get into a tight spot and they try to turn the wheel, that's where the torque is pushing the opposite way. So one last time. Driving down the road, okay, we want to make a right-hand turn, which means we want to fight to lean to the right, which means we need a mega going this way. To get that, we've got to apply a torque going up. And so we're going to apply a small torque on the steering wheel and push in the opposite direction. Our wheel's not going to turn that. We're going to apply a torque to create equilibrium. The whole thing will go. We need to bring us real. Okay. Or go out and ride your motorcycle. Think about it. Now, this isn't for parking lots for you, Jordan. And I'm not saying, you know, get on a motorcycle if you haven't done it and drive fast. Okay. Well, I fell 15 minutes behind time here. There are all kinds of interesting examples in case that can do. All right, so we're behind time here. Let's take a 2-minute break, and I want to do, you need to step out a minute, or I want to, let's just say a word about research. I guess we keep on. We're working on, nice time to start thinking that we're really going to program. Too much to say. It would be nice, well, a couple comments. I do want to start connecting with advisors. And we had our nice early meeting. Maybe one thing we can do is, maybe I could start having short meetings with, maybe over the course of the rest of the summer, I could sit with each of you a little bit. Maybe there's some news bad, I don't know, start connecting with it. I'm open for suggestions, but one thing I do want this summer is to start helping make some bridges to next things. If you had labs you want me to see again here Thursday, if you have labs or anything you want me to see, feel free to do that. And I suppose I could try to bring a colleague along at some point. I know we have a little meeting, but really the discussion was I just wanted to mention that I'd like to start helping you guys get connected to an advisor. You met our faculty last time. We've got a nice group. We've got a nice group of, a lot of young, active faculty. Some are younger than you, but, a little green behind the ears, but that's fine. They'll be good to work with. They're energetic, doing good things. I know a lot of interests are in the dynamics, vibrations area. From a dynamics standpoint, I think I'd be a good fit. Vibration standpoint, couple possibilities. Steve Anton, who was here and met, he's been doing some structural health monitoring. He's doing some high speed. He's got a nice project right now on high speed. He talked about high speed propagation. I think he's looking at the dynamic propagation in fire mechanisms, so they're can go high speed predictions and consistent. He's got a project on that, and it's going well. I will say, I think that we're pretty open to working with maybe research that you're doing. Tommy had mentioned an IR&D, an internal, you have had another name for it.
Same idea.
Same idea.
Yeah, smaller.
Yeah, well, but I think, in many cases, it probably makes sense to hit with something you're doing, and the advisor maybe kind of advise you on that along the way too. So I think what I'm going to do is on Thursday, I'm going to allow at least 5 minutes, not too long, because we don't have a lot of time, but open up time. Does anyone want to mention a project that they're thinking we could just discuss for a minute?
The other record that will open next week is the first time.
Right.
We're about to change it from being solid mercury to totally mercury.
Yeah.
Propagation of the circulation through that thing. So we got the strain instruments that we put on them.
And
we have that calibrated.
And they you say they die, but they give you good measurements.
Yeah.
At least they just don't last that long.
Yeah, we're due with the building.
So you've got good data there.
Yeah,
Yeah. Yeah.
They might find probably the
Sure. Well, no, we've committed to that. So we have committed. TT is committed to that. We might have to be exact. Somebody that's doing this day and night, but yeah, we've committed to that. Now that because you mentioned that one to me earlier, it might be, I'd say the word exercise, but it might be nice if you had projects, if we started doing a short write-up of that, I could kind of start sharing that around.
together.
I think so.
Anybody we can bring down here, I can walk around.
Yeah. If you have something that you're doing that you think would be a good fit, sharing that. I know we met one time, and we'll try to get down again. I think there's something scheduled again, but at the same time now, things go. An elevator pitch. So yeah, so if you were to write up a short thing, I think I could start sharing that around. Particularly other thing I'll tell about our young faculty is that they're motivated to get involved. They love an opportunity to kind of get some. Jason, are you gonna comment?
I was just thinking, there's a couple of masters or the PhD. So I don't know that that's feeling about the scope of the research part.
Yeah, yeah.
How much?
How big, how much?
How small, you know,
Yeah.
how does, you gauge that if something, idea was suggested, say, no, that's not good enough for this.
Well, yeah, let me tell you formally how it works. There's a two-level process, and this is, by the way, our PhD program pretty much looks like that. So I mean, there's little nuances, but the way the program works is pretty much the same everywhere. So you'll first get an advisor. You'll want to connect with an advisor, and so that's really one thing. I think even, and you know, if you haven't gotten to the pot, you know, it'd be good to start connecting with someone, have a little bit of relationship. You know, at least helps out. Right now, I think Dr. Rao maybe is signing off on whatever if there's something to be signed. So at a minimum, it could be, hey, here's a class to do. We're all taking that class. Here's a class. That would be nice. You have a little bit of a relationship, a little bit of communication, and then just get a feel for that. But to answer your question, the first thing you do is you work with the advisor and you start to lay out the problem. So the two of you look at it and see that's fruitful. Now, one thing I will tell you about research is if you knew exactly what the problem was going to involve and how long it would take, it wouldn't be research, right? It would be an engineering problem. You know, you did the thing. I know it's something. There's the one side. So you never really know at the beginning. Don't be scared by that, but it is always something that you don't know. So you and your advisor look at, you know, given, you know, your mutual experience, you say that seems reasonable. We kind of have some ideas that we're going to try, and you know, then we'll report on. You know, one thing in research, you don't say, I'm going to solve this problem because you never know, but you're going to study it, you know, ideally you solve it, or you get a different discovery you didn't expect one day. The second part of that is the committee. You make a formal presentation to the committee that reviews, you propose, here's what I plan to do to the committee. It's usually usually it's about an hour meeting. You make about a 30-minute presentation, depending. And then the committee, which is a 5-person committee, will review that. And there's an open discussion among the committee about the scope. Is it long enough? Is it too much? And what's involved? You also lay out a timeline. There's no timeline. In many cases, I honestly, as often as not, I see some de-scoping there. I generally don't see, usually, you know, who knows? It's got informed on. Okay, so that's the first thing. And then the second thing that I'll say is, you know, when I look at a master's degree, now it's a little more nebulous than the PhD, but we'll start with the master's degree. When I think about a thesis for a master's degree, I usually think that's about $1,500. And I make that, I mean, it is a made up number. But I tend to say $1,500. We have a non-thesis option, and this is just me. Other people have different opinions, but when I look across the board, it's increasing. Our non-thesis option, I'd say, is about a $250 to $300, and so there's a 3-hour class. And I figure somewhere between $200 to $300. You read something. I look at that 1,500 hours. Typically, I see, you know, a traditional student comes in. They're there for like 4 semesters, maybe a summer. And so if you figure, well, they're putting 10 hours a week in that first semester, and they build up to 20, maybe last semester, 30 hours. That's where they are. Or if you say, I'm going to go full time, I'm going to work 40 hours a week on this, you're looking at about 6 to 8 months. Usually there's some lead up time, and then about 6 dedicated months. That's probably, if you really start adding up all the time you're spending, I think that's somewhat reasonable. I don't see people that add up all the time getting a master's thesis. They just don't see that typically. I don't see them going way above and beyond. I would say that PhD is going to start looking more like that. You know, and this is why we want to find something that overlaps what you're doing, maybe that 2,000 to 3,000 hour time frame on that. So, you know, it'd be a year and a half of just steady work if you're doing it. Now, if it's something that part of your job assignment, you still want to make that. You know, the PhD, frankly, I've not thought about the hours as much. With the master's, I feel pretty good on that number. It's at 12 to 1,700 I see students. We like to see, it would be good to have some evidence coming out of the PhD would be a couple publications, you know, somewhere between, you know, 3 to 5 publications, maybe 2 journal publications, and a couple conference publications. I'm seeing that for, and again, I'm referring to this. I don't have experience really with what we're doing. This is new. It is new to all of us a little bit. We're figuring that out. But if I look at a traditional PhD student, I think that's pretty common. that they'll have either, either papers that are published or pretty strong papers are submitted. Maybe they've been accepted or they're under some review process. I think that's pretty typical. If you took, I'm thinking of a kind of a recent case. If you take a case where somebody's got maybe 2 journal publications, maybe one's been accepted and another one's in the pipeline, it's strong. And then maybe a couple conference publications. And again, this is for a traditional student. Often then that 5 to 8 thesis, chapter thesis starts looking like, chapter 1, 2, introduction, but then chapter 3 is like chapter 4 is maybe the body of the paper. So you've got like 3 papers that are really the chapters. And then if you look at a paper, oh my goodness, sometimes papers become time drains. Yeah, they take some time, but you kind of have a handle of what a technical paper starts to look like. And if you're not, okay, I'll put this first. So this is the last thing I'm going to say. If you're not involved with looking at papers, writing papers, engaging, I just don't know how it works, but that would be one activity that I encourage you to do with your colleagues, to be connecting with an advisor, start thinking about a paper, even a conference paper. Conference papers are easy. You guys have the ability to take conference. Yeah. So, you've got to be careful. You have bad experience with conference? Okay, you go to a lot of conference.
It's fun.
Exactly. It's fun. There's no problem finding it. You probably right now you're receiving a mail saying, "Hey, come to."
The other side of the coin is that, there's some unclassified work that is achievable and doable, but all that, for most of the people in this room, well, for a good majority, it's going to be classified.
Yeah.
And that makes it exceptionally hard to find something that, number one, we can do. Number two, we can get an advisor that may or may not be a foreign action.
That's going to be the toughest nut to crack. So let me a final word be that let's look for a way that you think of some published unit that's iTalk, that's the iTalk maybe the next time we get together, somebody that's maybe participating in some, maybe you can talk about some experience of how you get through ITAR, how you think about it at the beginning. I do think that if you started that publishing, Jason, your answer, if you walk into the committee and say, hey, conference papers are not the same archival merit, just in general, often being, but if you walk in and say, I got 3-4 conference papers and this journal paper or 2, it's hard for the committee to say you don't have a body for it. And it is measurable. And I'm making up the numbers, but I think now that we talk, looking at if there's a way that your group that you can publish something. There are some meetings maybe that are there's some meetings. I'm on the RSD committee under ANX, and we host a meeting every other year. And there are some sessions that are employees in that.
It's just hard with the fact.
Let's next week. Can you talk a little? Because I honestly am not well versed. I've had the IRD training, but the IRD training. Maybe next week you could say a couple quick words on that. Okay. And then anyone else could bring something. But if you don't mind, maybe you could comment or two, share something. Okay. Other thoughts on that? Okay. Euler's rotational equations. Probably should have paused the recording for that, but yeah. That's the thing about the PhD. It is a mindset of research, and we are in a long journey. I do think that if you can start to integrate some of that new normal activity, clearly, you guys have been approved to do this. You maybe have a little. I don't know your situation. Maybe there's a little leverage. You can say, okay, I need to participate in a conference and do this for you. Maybe it's a paper that you're doing. Maybe you're a little outside, but you're contributing to another group. We'll communicate next week. Okay. So pulling it all together, we have Euler's rotational equations and Newton. Newton's equations. Okay, and I'm not going to rewrite this. There's 2 special cases for Euler's rotational equations.
You can see these from derivation. I'm going to tell you there's two special cases because everyone says there's two special cases. I frankly only use one of them, but there are two special cases. So the first case is that D is equal to DG. In other words, D is the center of mass, which implies that DG equals 0, which implies that M about G equals IG alpha plus omega cross IG omega. And that's the form that I like. I tend to use. I think that's the most common form people use. The second special case is that D is a fixed point. I frankly don't use this, although it's handy at times. And you could see if you could actually go back through the derivation and then show that. I'm not intending to here, but you could. It could be shown. So D is a fixed point. And in that case, the moment about this fixed point, the sum of moments, these are all sum of moments, is I about the fixed point alpha plus omega crossed with I about the fixed point omega. All right. I hesitantly, I will not use that one in our class. I mean, you can, and you'll see the examples, but I tend to just stick with the first one. All right, so two special cases, subsets of that process. Next, okay, let's expand Euler's rotational equations into matrix form. And now from here on out, by the way, from here on out, I'm going to write Euler's rotational equations about the center of mass. So mg, yes, I never shut it off. Thanks for reminding me though. I probably will shut it off for our little conversations. Keep reminding me though, I do not want to lose that. IG alpha plus omega cross IG omega. All right, so when we expand, we get M1, M2, M3 equals I. So I'm just writing the terms here. I'm not going to write them all out. So it's just I subscript, and the subscripts are row column. So I11, that's row 1, column 1. I12 is row 1, column 2, and so on. Times alpha plus. Now, I'm going to use, recall last class, I mentioned that you could take this cross product here and turn it into a matrix, a multiplication, a matrix multiplication. And we said that if you take this, if you take a vector, expand it into a skew symmetric matrix, and a omega cross is equivalent to the skew symmetric matrix and omega cross. So effectively, I'm now going to say skew symmetric matrix of omega times IG omega, and then that becomes the skew symmetric matrix is zeros on the diagonals. The upper diagonal is negative omega 3, positive omega 2, negative omega 1, and then positive omega 3 on the lower diagonal, negative omega 2, positive omega 1, times this I, and I'm getting a little cramped here as you can see, omega 1, omega 2, and this is the IG. Okay. And again, don't forget that this is about the centroid in body fixed coordinates. Okay. Next, I want to write down Euler's, and this is Euler's rotational equations. So now I want to look at Euler's rotational equations, for a principal I. And I haven't talked about the properties of I yet, getting a little ahead of myself, but a principal I. A principal I is, so this is IG principal, is an I that's composed of the principal moments of inertia. And I'll call those I1, I2, and I3. I get zeros everywhere else. I see that I'm jumping the ball here, but let me write this out. In that case, I get M1, M2, M3 equals, actually, let's write it like this. Let's expand it out. In the interest of time, I need to do that.
I'll put in principal I here, so I get this is diagonal times alpha, this way times diagonal times omega. When I expand that out,
And when I plug it in, I get M1 equals I1 times alpha 1, which I'm going to call omega 1 dot. Okay, that is alpha 1. It's just the time derivative of omega 1. Minus I2 minus I3 times omega 2 omega 3. M2 is I2 omega 2 dot. And again, omega 2 dot is alpha 2 minus I3 minus I1 omega 3 omega 1. You can see a little bit of a symmetry or a pattern here. M3 is I3 omega 3 dot minus I1 minus I2 times omega 1 omega 2. Or you can set this back up and solve in terms of omega 1 dot, omega 2 dot, omega 3 dot, which is, and I'm not going to write all these out, but the first one would be I2 minus I3 all over I1, omega 2, omega 3, and so on. Okay? Frankly, taking Euler's rotational equations around the centroid is the most common, and frankly, using a principal moment of inertia matrix is the most common. I need to say a word about that before we part. So this form is a very common form. Okay, so this is a common form of Euler's rotational equations. You can leave it, you can leave it in the vector form above. Here you have it explained out. All right, when you're solving dynamics, remember we talked about two ways, two directions. Given the motion, solve for the forces, I call that kinetostatic, or given the forces, solve the motion. Some people would, I call that inverse dynamics, some people would call that true dynamics. It doesn't matter to me. But typically, you're solving simulation problems. You've got an input to your system, a motor, you've got an input to the system, and you want to propagate it. So you're solving this, what I'm calling the inverse dynamics problem. Note that you get differential equations in that case. Here are the differential equations, right? So here they are for Euler's rotational equations. And then if I were to, if I were to write F equals MA as F equals MX double dot there, right? You would see here that I've got my differential equation. So I'd have that for the X, Y, and Z. Maybe I should call it R double dot. And I'm being kind of sloppy there because we realize how much is involved in kinematics. All right. N2, second order differential equation, right? Let's keep you loud. Euler's rotational equation. First order differential equation. You see that? That first order differential equation. So when I write this, when I write my Newton Euler equations, I get basically 3 second order differential equations. And here I'm using O to E to be order differential equations. I should put a little or there, not ordinary differential equations, although they are that as well. And I get 3 first order differential equations I get from Euler. These are from Euler, and these are from Newton. All right, now, how many differential equations do you think I want? How many do you think I need? I mean, this is, well, okay, let's back up.
3 second-order differential equations, 3 first-order differential equations. How do I typically deal with it? I typically deal with it by casting into state space, or just casting it into a series of all 3 different differential equations. So I just add intermediate terms that, and we'll do that a little bit in review, but I just add intermediate terms. So in practice, I'll cast this into 2 times 3 or 6 first order differential equations, and then that gives me 3 first order differential equations. Okay, so there I've got 9, right? All right, back to my question. How many first order differential equations do you think I want to solve the dynamic of a rigid body equation? Wow. 0, you can't have it. 0 works clearly, but not now. 12, any 12. Because, you know, we live in a second order world with dynamics. And so I've got 3 rotations, 3 translations, 3, you know, I've got 6 terms times the second order, so I need 12. So there's 3 missing here, right? There's 3 missing. The 3 that are missing come from this whole issue we had of, remember I mentioned non-whole, omega is a non-holonomic vector. You can't integrate omega and get a beta. You can't integrate a vector and get a non-vector. I mean, that's the whole problem, okay? So we need 3 more, just as you pointed out, we need 3 more. And, you know, all this stuff is beautiful. The 3 more are a little bit clunky, but we'll get the 3 more from what I call, and I need to find a formal name, and people avoid naming it. So here I've named it Euler's angle equation. And that's what Canfield calls it, okay, by S. Canfield. And we'll have to obviously pick that up next time. But there are 3 more that are going to come from that. That's pretty straightforward. But here is the Newton-Euler formulation. We've done everything but an example, and we didn't talk about it. That's what I have to do Tuesday. So plans next week. Well, first of all, I'm not going to talk. You guys have questions about Newton Euler equation. Anything in the notes that we didn't clarify? Any quick questions, observations, comments on that? Okay. The next thing we need to do is I do want to review properties of I, which I that we derived, that we know is out there, but we'll take a few minutes. I want to review that. I'll show you Euler angle equations, right? The remaining 3, how we get those, and then we'll do examples. We'll do examples. I would like to, that'll be our plans for Tuesday. And then I don't know how well MATLAB worked for you, but I'll try to see if I can do a little MATLAB stuff on Tuesday. I can't run MATLAB very well here at the moment. It would be nice, but did that work okay? Were some of you able to have MATLAB? Okay, well, I'll try to do a little MATLAB on Tuesday as well to practice along the way. All right, homeworks and collecting homeworks, and then I will post my job before today or tomorrow to get the next sample and homework set up, and it's coming from the next step. Well, let me get it up today and make it do next week. Let me get it up today and make it do next week. It will be practicing rotation operations, and then that acceleration, that problem I got hung up on. There'll be figures about 3 of those. So
what videos would you recommend to watch?
You know, I'm catching up. We basically caught up with the video. I've got it. So at the moment, I'm not working with the video. I do have a few more. I don't have it. So the next class I'll read it. I'm caught up with this. I will try to get something together.
Those things are good.
Are they helpful?
Are they? And have the notes. I see a lot of guys start on the notes.
I don't know, print it out beforehand. Yeah.
Well, I've got to get organized. So yeah. Okay.
That allows me to watch. Yeah, last semester.
Okay, here, let me